All right, so welcome everyone. My name is Grace O'Malley and I'm the project manager or facilitator for this project from the iNEMI staff. And both Richard and I will be co-presenting today on this call for participation webinar for the new project on board level optical interconnect performance in immersion-cooled environments. I'm going to start, or we will start just quickly. The agenda will give a brief overview of who iNEMI is. Perhaps not everyone is familiar with the consortium. We'll talk a little bit about the project process, how it came together, the state where we're at right now. And then I'll hand over to Richard, who will talk about some of the drivers and background and context for the project, the project objectives and the plan. And then at the end, I will give more details on how to join the project and how you can get more information on joining. Hopefully, we'll have a little bit of time for Q&A. You can, as we go through the presentation, submit your questions via the chat function, if you would, please. So for those of you that don't know, iNEMI is an industry consortium, very much industry-led by our nearly 90 members now worldwide. And as you can see, they're drawn from all across the electronics manufacturing value chain, from device suppliers, fundamental materials and equipment suppliers, academic institutes involved in all aspects of electronics manufacturing, through to EMSs and system integrators, and all concerned and interested in working together on common problems that impact electronics manufacturing. We are a not-for-profit organization and have been actually around for nearly 30 years now. Many of you will be familiar with us through the projects which help address some of the technology and infrastructure gaps in the industry that are preventing, new technologies going into high volume deployment. We're also involved in road mapping the future technology requirements of the global electronics industry as well. In terms of the project, which is really I suppose, the most benefit that our members get is being involved in these collaborative projects that are very much focused on common pain points for the industry, not working on technology development, but how to enable technology to get into high volume manufacturing. So they typically are addressing a gap or a challenge in the industry that is best served by an industry collaboration. We try and bring together representative capabilities from across the electronic supply chain to address these. And usually they're in alignment with the members' companies' commercial interest and plans for the future. Our projects typically are about 12 to 18, maybe 24 months long, depends on the project and the scope of what's being done. And typically membership is required for participation in all our projects. All during the planning process, or the initiative process as we call it, non-members can participate. And indeed, we saw this on this particular project where we had 9 to 10 companies very active in the discussions as to what might be the scope and objectives of this particular project. And in this particular case, we've structured the project for a 12-month plan, which will allow non-iNEMI members to participate under certain conditions. Excuse me. In terms of the outputs of the projects in general, everyone produces a report out to the members initially, and often papers and presentations to the industry. But in addition to that, they often have other outputs such as development of software tools, development of data, which can help in, for example, in this case, in refining modeling capabilities and development of modeling tools. It may also be inputs into either existing standards or recommendations for the need for new standards development. This next slide kind of gives a quick overview of some of the more recent examples that have come out, including recommendations on sample sizes for industry test methods in the area of 5G, looking at best practices for data center interpretation of expanded beam connectors. We've also looked at developing software tools, looking at life cycle assessment. So really a broad range of outputs that come out and reflect the needs and interests of our members. Our projects, as I mentioned, are really driven by the needs of the industry and focused by the needs of the members. So we have a project development process outlined here. We've just completed the initiative or planning phase, and this does have review processes as we go through it. We're reviewed by the technical committee within iNEMI, and as we go along, we're building the team, refining the project plan and scope, and assessing the resource requirements, etc. And that's what we'll be presenting today. We've reached that point where we're just pre-launch. And as we go through this, we found this process to be very, I think, effective over the last number of years in helping us, I think, launch the projects much more successfully, in that we've a lot of the planning work well defined in the initial stages, and resources defined and committed before we start. And indeed, that's an important thing in this particular project, where we have a very aggressive timeline of 12 months. Once we launch and move into the project phase, everyone who participates in this must be an iNEMI member or be able to participate under some agreement with iNEMI. And I'll discuss more about that a little bit later in the talk today. But for now, I think the key things that you guys need to understand is we've created a plan. We call it a statement of work, and also a project statement, which is the commitment document that all the organizations participating sign to give a commitment in terms of any resource and time contributions to the project. All of this information is available now on the project page, which is on our website, and you can get that through the link here. I'll discuss this part in a little bit more detail as we come to the end of it. But again, there'll be slightly different processes for iNEMI members and non-iNEMI members as we go through. All right, so with that, I'd like to hand over to Richard, who's going to take us through an overview of the project, the motivation for the project, and what the plan is.
Thank you very much, Grace. Okay, well, just to give you an overview of the context of this, this is targeted at hyperscale data centers, and power consumption of data centers on a global scale is significant. So if we were to take the global collective power consumption of all data centers, that would be larger than the entire power consumption of the United Kingdom. So immersion cooling is one disruptive solution to try and substantially reduce power consumption in data centers. In essence, by providing an alternative to fan cooling, which consumes a lot of power. Another one is optics. Optics can provide a reduction in data center power in many different ways. One of the ways is by introducing new faster architectures, optical architectures such as WDM architectures, and other ways are co-packaged optics, is where the optical transceivers are brought into the box very, very close to the signal source. And you may have heard about co-packaged optics. So one important thing is what happens when we put these two together. If you have immersion cooling and embedded optical interconnect, we're seeing this convergence, this natural convergence happen, but we need to understand what the knock-on effect is. And the purpose of this project is to understand what happens when we bring all the normal, the ecosystem of optical interconnect technologies that will be expected to come into the system. What will happen when we actually bring this into an immersion cooling environment? Okay, so the objective of this project is to investigate and evaluate different optical components, active and passive, with different representative immersion coolant environments, and to understand how this affects our choices for optical interconnect in the future. Next slide, please. So the strategy will be to we'll be working with providers of optical components, optical connector companies, optical cable companies, micro optical component companies, and companies providing and developing immersion coolants. And so our strategy will identify and acquire representative selection of optical components. So we'll get a selection of the most common optical connector technologies, cables, and optical coolants. And we will assess how they work together. We'll develop test methods, build on existing test methods, or develop new test methods to allow us to really fully evaluate the performance in different ways of optical connectors and optical interconnect in these different immersion coolant environments. We'll be looking at long-term testing, so more than 5 months, and we'll be looking at accelerated testing, where, for example, we heat up the coolant, but we test for a shorter time, and we'll be comparing those. We'll also be identifying and determining methods for mechanical and optical testing of the components. We'll be using common methods such as insertion loss testing, return loss testing, and we'll be doing mechanical testing so we can test the modulus, the volume of components if there's any volume change, swelling, the surface texture, and we'll be looking at contaminants that may leach into the coolant. And one outcome of this is we want to identify valuable, useful test methods. Again, they may exist, we can choose, or we may have to adapt current test methods to make something very, very suitable to evaluate optical interconnect in these immersion-cooled environments. And we'll secure the right fluids and test chambers. Next slide, please. Outputs of this, the outputs we expect for this project is we will gather data, we'll gather test data on how these optical components perform in these different environments, and we will publish certainly an internal report, and most likely, depending on the impact, we want to publish a paper. It could be an open conference paper, or preferably a journal paper, which summarizes our findings after a year. This is a one-year project, as you'll see in a moment, so we want to summarize our findings in this kind of application. We'll also be reporting on potential test methods, on the most useful test methods for these immersion cooling environments, which which will be useful, of course, for different companies to use. And we will report on the evaluation of how the different coolants have performed. One important outcome of this is, of course, that we recommend to relevant industries. We recommend the requirements for how system integrators, for example, would develop onboard optical ecosystems with immersion cooled environments, and what they must be aware of. And finally, we'll also be reporting to primarily the IEC, but also the ISO and the ITU. But in any event, the IEC, with a view, depending on our findings, to modifying existing standards, or preferably developing new standards for testing in immersion cooled environments. Next slide, please. Benefits to participants are we'll be leveraging the resources of the collective resources of our different participants, bring them together in order to carry out testing and to share the results. We'll be increasing our collective knowledge on the impact of immersion cooling, of what happens when we bring optical interconnect and immersion cooling together, and we'll be identifying the most useful test methods. For example, acceleration factors for testing. We'll be comparing, for example, different acceleration factors with long-term testing to see what is the most realistic way of evaluating the long-term effect of components within immersion coolants. We'll be enabling faster materials development, and we'll be enabling faster industry standards adoption. Next slide, please. So, test regime overview. We'll have three phases, three test regimes. The first test regime will be looking at individual components. So this could be individual parts, connected parts, sections of optical cable with sheathing, micro lens arrays, thermoplastics, glasses, the individual components, and we'll be testing them individually, passively, with different immersion coolants. So what happens is that before and after, we'll put these components into different immersion coolants. We will look at the mechanical properties of the components. So what the hardness of the surface, the volume before and after, and we look at whether being in the immersion coolant has caused it to swell or caused it to soften, And we'll be looking at the coolants themselves to see if the before and after, to see if anything has leached into the coolant. So this is very, very important. Test regime 2, this is where we look at mated connections. So in these kind of systems, you always have optical connections. You'll have patch cords connecting to each other using standard connector interfaces, and we want to look at how these connector interfaces perform under immersion coolant conditions. Will there be wicking of the immersion coolant into it? So we'll be looking at, we'll be measuring the performance insertion loss and return loss before, after, and during immersion of these of different mated connectors. And that's quite important. And then finally, test regime 3, we'll be looking at active devices. That means optical transceivers. So we'll take optical transceivers on evaluation boards and we will immerse them. And there we won't go into detail, but we want to characterize the performance of the transceivers before and after and during immersion to see if it makes a difference. For example, depending on your coolant, the dielectric the dielectric constant of your coolant, it might have an effect on the signal integrity propagation on the PCB, which is holding certain transceivers. That's an important thing to know, and indeed it's been observed before. So that, for example, that would affect your choice of dielectric constant of your coolant, and we'll be looking at other things as well. Next slide, please. Here is the project plan. This is for the 1 year, the 1 year fast turnaround. First of all, second there, let's look. First of all, we will develop and finalize we'll agree amongst our partners the experimental procedure and the checklist for these 3 categories, these 3 test regime categories. And that'll happen in the first 3 months. And in month 2 to month 4, we will prepare the test bed. So we're preparing for the experimental assessment and for test regime 1, 2, and 3. Test regime 3 it's a little more complicated. So that'll be month 2 to month 5. And then the crux of the work will be the execution of test regime. So this will be the testing that we carry out. So for test regime 1 and 2, this will be month 4 to month 9. And for test regime 3, this will be month 4 to month month 10, I think, month 10, not month 9. And also results comparison. So then we look at we'll analyze the results and we'll generate internal reports. That'll be month 7 to month 10. Socializing the project results. This is where we engage with standardization bodies. So we'll report to the IEC. And then we'll formalize our publication of results in a conference paper or a journal paper by the end of the project, where we summarize all our findings. And then as usual, we will have an end of project webinar at the end of month 12. Next slide, please. So test regime 1, just take a closer look. This will be looking at individual components. We've shown some examples here. LCSCR, MT, and MPO are all the connector types. So we'll be testing those. There are new connector types such as SN and SNMT, which will be considered, and others which are offered by our connector companies. Contributors here are our mainstream optical connector companies: Samtec, Semtech, Sumitomo, Hakusan, Molex. And micro-optical components here, we'll be looking at glass and thermoplastic such as microlens arrays. And here we'll be looking at contributions from companies like SABIC, who make the thermoplastics. Test phases here will be pre and post immersion. That means we'll be testing the components mechanically before and after they've been immersed. So we'll be looking at the volume, we'll be looking at the hardness of the surface, and the coolants themselves, we'll be looking at the cleanliness of the coolant before and after. So that way we can see if there have been any physical changes in the component and if there have been any chemical changes or contamination of the coolants. Next slide, please. Test regime 2. So this is where we look at slightly more complicated, where we have mated optical connections. So we take common optical connector types with patch cords, and we will submerge the mated section, only the mated section of the patch cords, into different coolants. The other ends will be out of the coolant, and they'll be used for standard testing of insertion loss and testing of return loss. And this will happen before immersion, during immersion, and after immersion. So we want to look at changes in performance Changes in performance would indicate, is there a chemical change which is changing the alignment? Is the bore holding the fiber swelling, causing misalignment, and all these things. So we'll be looking at all these important factors. Next slide, please. And test regime 3, this is where we take more complex active devices. So we take common transceivers are SFP or QSFP double D, or some of the experimental transceivers that are being considered for co-packaged optics, microtransceivers such as the IO core transceiver, which IO core already presented, and other COBO mid-board transceivers if they're available. And we will have them on evaluation boards, and they will be submerged. And we'll be using common characterization techniques to look at the performance of the transceiver before immersion, during immersion, and after immersion. So has immersion changed the performance of it? So this would be generating traffic, running it through the transceiver with a loop back, looking at bit error rates, or maybe a communications optical signal analyzer, depending on the resources of who's testing it. But here we want to look for any changes over immersion. Next slide, please. Resource requirements are, depending on the organization, we need optical connector components. Here we've listed common optical connector types. We need micro optical components such as micro lens arrays, and maybe ferrules by themselves and sections of optical cable. We need mated optical connectors. So here we need patch cords, which can be tested either end with different connector types. Probably the hardest to come by, but also very important, is optical transceiver evaluation boards. So that's not just the optical transceiver, but it's the evaluation boards, because we need to run the transceivers under immersion coolant conditions, and we need to measure changes in their performance. We need cooling liquids, of course. We need a representative selection of different immersion coolant types, single phase mostly, but also dual phase if it's available. We need access to testing tanks. So depending on the requirements of the immersion cooling environment we're emulating, this could either be flasks that are provided to different component manufacturers very easily, or it's specialized testing tanks which are provided by the coolant providers themselves, or universities or institutions looking at this. There'll be chemical testing of liquids before and after testing. That's important. There'll be testing of the mechanical properties of the components, hardness, and volume, and there'll be the means to carry out optical performance measurements, such as insertion loss measurement and return loss measurement. Next slide, please. Okay, I'll leave it to you, Grace.
Great. Thank you very much, Richard. As I mentioned, if there are any questions, please put them into the chat function, and we can address those as we go on. But before we finish, I'd just like to give you an idea how you can join and participate in this project. As I mentioned, once the project starts, we need to have an agreement of sorts with each of the participants. We've run 2 webinars now to give people an understanding of what's involved in the project, and we're opening the sign-up period until May 26th. So if you are interested, please let us know before then. The project will probably kick off in June, depending on who's joining and agreement on the start date. It will run for 12 months, and right now we're planning to hold 1 hour-long meeting every 2 weeks. It'll be hosted on Teams. It will be recorded, minutes will be issued. So if people miss, a couple of meetings along the way, they'll have an opportunity to catch up and have access to what's been discussed in each of the project areas. Now, as I mentioned earlier, the project has a project page on our website. You can find it by just going to iNEMI.com and looking through the projects and look in the projects in development part of the website, and you'll find this particular project, or this link will take you there directly. iNEMI members will know that in order to participate in a project, they should review all the relevant documentation and return a signed project statement to me by the 26th of May. Non-iNEMI members are allowed to participate in this project under our fast turnabout status that has been established by the board. This allows non-members participate in one iNEMI project at the time. They are required to obviously review all the relevant documentation, return a signed PS, and in addition, an MOU will be required, again, outlining just I suppose, the rules and regulations for participation in an iNEMI agreement. And also there is a fee associated with that as well. iNEMI members are paying an annual fee, which is relevant to their revenues in the area of electronics, but we have a special much lower fee just for this one-off participation in the project. This resource requirement that Richard mentioned earlier is actually included in the project statement. Our projects are typically self-funded by the project participants, and we also want to include a good representation of the different types of components and optical connectors and optical assemblies that are of interest to the industry. So we have included this resource requirements in the PS document so people can indicate where they might be willing to provide either services or components or materials for testing. I mentioned the fast turnaround participation for this project, but it only lets you participate in one project. So if there are non-iNEMI members who might want to consider participation in other iNEMI activities and projects, you can review that information and the associated fees and requirements on our website as well, or please feel free to reach out to me at any time and I can get you further information. So with that, I will just check and see if we've got any questions today. Richard, anything else you wanted to add?
No, nothing more from me.
Okay, great. Thank you. I don't see any questions coming in, so hopefully we've managed to answer them all. But if any occur to you, please do contact us directly. Particularly if you're interested in the fast turnaround, you'll need to contact me directly as well to get further details on that, and so that I can give you the right documentation and information that you need. So again, if you are interested, please feel free to let us know so we can start those discussions earlier and get everything completed by the end of May. All right. Okay, I think that's it then for today. Thank you all very much for your time. And please do check out the website for this and other iNEMI projects. And hopefully we will look forward to working with some of you on this project in the future. Thank you all very much and have a good day.
Thank you, Grace. Thank you, everyone. Bye-bye.
Thanks, Richard. Bye.